Okay, so like I said in the last video, you can always do this limits with the table and just start plugging in numbers closer and closer to the value. But that gets a little tedious after a while. And like the trig one we did doesn't always necessarily work out where you can figure that out. Although the methods I'm going to show you today wouldn't necessarily work with the trig one either. The trig one was just a little bit goofy. Okay, the first method is by direct substitution. If you can plug in the value and a is in the domain of the function, then unlike the graphs that I was showing you where they weren't necessarily equal, the limit as x approaches a of x should equal the same as f of a. So that only applies if a is in the domain of the function. Most of these problems, 90% of the problems I'm going to give you, maybe 95, actually don't have a in the function because those are the more interesting limits to find. But if you can plug it in, you should. For example, looking at these two, on this first one, I plug into? Is 2 in the domain? Is there any issue with plugging in 2 into this first function? I don't see any issue with it. We have 2 squared plus 6 times 2 over 2 to the 4th plus 3. So let's see, what does that turn out to be? 12 plus 4, that's 16 on the top. 2 to the 4th is also 16 plus 3 is 9. So that's 16/19. The nice thing about direct substitution is if I tried to plug in numbers close and close to 2, would I ever get to the being the limit is 16/19? I'm not exactly sure that you would be able to do that. You'll not get that. You might think it's closer to 1 or closer to 3/4. You wouldn't get exactly 16/19. So these are a little bit more exact methods. The problem with this next one, and this is what the whole if it's in the domain, if I try to plug in 4 here, I get a 0 in the denominator. So 4 is not in the domain. So we can't do this one with direct substitution. There are other methods we can use, but we cannot use direct substitution. We can't just plug in 4 and see what happens. We get 4 minus 4 over 16 minus 16. That's 0 over 0. We can't figure out the limit from that. We have to figure out something else. Okay, so here are some other methods, and I'm going to go through one problem of each one. I did a one-sided limit one already in the last video, but here are some other methods to use. The first one is factoring and canceling. You guys did this in Algebra 2 when you were finding holes. It's the same idea as finding a hole. You factor and cancel. The idea of all of these is you do these and then you do direct substitution. So the first method is factoring and canceling. Second one is just simplify things, see if you can get that denominator to cancel out. The fourth method is a little weird. It's called rationalizing the numerator. It really works out nicely and things happen quite nicely when you try to rationalize the numerator. And then the last one is try to find one-sided limits. This one specifically applies when you're talking about piecewise, which we already did in the last video, so I'm not sure I'm going to show you that example again. But that works for piecewise functions. Okay, so going back to that second example where we can't just plug in 4, some of you are probably sitting at home going, well, you could have factored the bottom. And that's the idea of factoring and canceling. If we were in class and if you were taking a quiz on this, and when you get to calculus, Mr. P is going to expect that you write the limit as x approaches 4 for each step that you do because you're finding a limit. It would be like how some of you don't like to write the fraction till the very end, and I don't like that either. The limit is a mathematical operation. If you ignore it and then enter it in, it's not equal. So if you're going to be doing these types of problems, you need to enter it in each time. So the idea of factoring and canceling is I can see that the denominator factors, and then I can cancel those out. So the limit as x approaches 4. Now I got rid of the issue in the denominator, and I can plug in 4. Once you plug in 4, then it's no longer the limit. You're finding the limit. So the answer is equal to 1/8. But you don't have to write limit at the very end. It's just until you take that limit, you have to write it. So that's an example. Yeah, you've done these in Algebra 2 where you factor the numerator, factor the denominator, get something to cancel out. Usually the thing, because these are limits, usually the thing that cancels out is the issue in the denominator, and then you can continue on. Okay, some problems like this come up a lot when we do derivatives later. So it's a common issue with h approaching 0 and h is in the denominator. That's also a problem. But what you can see is you can simplify the top. So we are going to multiply out 4 plus h squared. That is 16 plus 8h plus h squared minus 16 over h. These 16s end up canceling out. So when that happens, you get 8h plus h squared over h. Well, you can cancel out, now that all three of them have an h, you can cancel it out. The limit as h approaches 0. Now that that h cancels out, you have 8 plus h, and now you can plug in that 0. Direct substitution is always one of these things that you're going to end up doing. So the idea of these methods is to get the denominator fixed, I guess is the best way to put it, so that it's no longer an issue. You're canceling something out so that you can do the direct substitution. I feel like I'm going through these a little fast, but the good news about videos is you can find extra ones of them and you can rewatch the video so you can see if it makes more sense after you see it a second time. Okay, this method is weird. I'll just tell you that right now because you don't normally do it. We teach you rationalizing the denominator, but really you don't rationalize the denominator very often in calculus. You rationalize the numerator. So it's the same idea. You have to multiply by its conjugate. The multiplying by its conjugate is the square root of x plus 1. So by the way, I'd first check to make sure I can't plug in 1. If I plug in 1 right here, I'd get 0. That's a problem. When I see this square root at the top, I think about this method, the square root of x plus 1. To do this method, limit as x approaches 1. Do not multiply out the denominator. Leave it as x minus 1. No matter how complicated and ugly the denominator is, leave it ugly. And then you do multiply out the numerator. So the square root of x times the square root of x is x. The middle two terms, that one and that, whoops, that's the same one. That one cancel out, and then you get x minus 1. The reason you don't want to multiply out the denominator is now you have an x minus 1 on the top and an x minus 1 in the bottom. Whoa, that was crazy. And they cancel out, which is what you're exactly looking for. So then you have the limit as x approaches 1 of 1 over the square root of x plus 1. And by canceling out that x minus 1, look what happened. You now can plug in that 1. So it's equal to 1. See how I dropped that limit right as I starting to plug it in? So this is equal to 1/2. So rationalizing the numerator is something just to get used to think about. You multiply by the conjugate of the numerator, and you multiply the top and the bottom by that same number. Don't multiply out the denominator, but multiply out the numerator, and usually something will end up canceling out. You can then do direct substitution. Okay, this is what I was talking about with left-handed limits or one-sided limits. For this problem, I would find the limit as x approaches 7 from the left of f of x. You need to have something that follows that limit. Don't just write limit equals. That drives me crazy. Luckily, you guys don't have to write it out, so you won't have that chance to drive me crazy. Sorry. And you'd find the right-handed limit and see what it equals. This is that idea of just plugging in numbers. So the right-handed limit would be plugging numbers into this function and seeing what it equals. And then the left-handed limit would be that one, seeing what it equals and seeing if they're equal. If they're equal, then you would then they're the same. So if I plugged in 7, could I plug in 7 to the right-handed limit? And now I figure I might as well go ahead and do the problem. If I plug in 7 up here, I get 0. You can do direct substitution with right-handed limits. The thing is you have to use both sides and see if they're equal. If I plug in 7 into this bottom function, I get 28 minus 4 times 7. That's also 0. If these two numbers were not the same when you plugged in 7 into both of these, then you would have to check. But the limit as x approaches 7 of f of x, don't just say limit equals, is equal to 0 here, because when I plug in direct substitution into both of these, they equal the same number. Okay, I think that's it for this week. One more week of stuff for those of you going to calculus. Otherwise, this is it. And then your Delta Math assignment. So why won't it cancel my PowerPoint for me? There we go. Then otherwise, that's it.